Hi, so this is Mohit Iyer. He's a graduating PhD from University of Maryland with Hal DeMay and Jordan Boyd Graber. He's done a lot of really cool work. He worked on this quiz bowl deep learning question answerer that won the competition with humans. He got NACL Best Paper in 2016 for some of the work he's going to talk about today. He was an intern with Scott and Ming Wei and got an ACL paper for question answering. Apparently, he's also been working with Pushing, which I didn't know until this morning. So yeah, he's got tons of cool stuff, and he's going to tell us about it.
Great, thanks, Jacob. Yeah, so today I'm going to be talking about how we can solve a variety of problems involving creative language using deep learning. And so by creative language, I mean text like novels, short stories, comic books, and these sort of character-centric narratives. But before I get into that, although Jacob has already said a lot, I wanted to just introduce myself in a little more detail. So I'm currently finishing up, hopefully the first week of June. And I started my PhD working on primarily deep learning for question answering. So I'll talk a little bit about this in the first part of this talk, but over the past couple years, I've sort of diversified and now also work on these more creative and multimodal problems, which will be the focus of today's talk. And just briefly, before grad school, I was an undergrad at WashU in St. Louis, where I spent the first 2 years as a creative writing major, and then decided that the job prospects were pretty dim for that field, so I switched over to computer science. But it's been great to sort of return to this and from a completely different perspective over the past few years. Okay, so I just wanted to start by introducing I guess a couple of NLP applications in which deep learning has sort of revolutionized the task and set state-of-the-art performances, and then compare this to the sorts of problems that I'm talking about involving creative language. So basically, I'm going to use this example sentence here. Arthur shall strike the blow that sets Lucy free. This is a sentence from the book Dracula by Bram Stoker. And so if we take the traditional deep learning framework, I can encode this sentence using some sort of neural network. And then I can train this to perform a bunch of different tasks. And so I can do things like named entity recognition, where I identify Arthur and Lucy as being people. I can do parsing, where I'm extracting dependencies between the words in the sentence, or translation. So here's the German translation of this sentence. And I can even do things like question answering, so I can have an additional input who wrote this sentence and train this network to predict the author, even if it has some sort of external knowledge base. And so these are all four very well-studied problems in NLP. And to train these networks, we need a lot of data. And so the data for all of these sorts of tasks comes from these sort of standard sources. So news articles, broadcast, new transcripts of broadcast news, and so on. And while these sources are very good for these low-level, like sentence-level tasks, they sort of struggle when we're looking at problems that involve high-level, discourse-level context. And so as an example of this, I may have this question: what does Lucy need to be freed from? And now I can't just answer this question by looking at the sentence in isolation. I actually need to understand the context in which the sentence was written in. And the point here is that context in these creative works is much more complicated than what you would find in like a news article. So this particular sentence, the context is the entire book of Dracula that preceded this sentence. And so I have things like characters, right? I have to understand who Arthur is, who Lucy is, what the nature of their relationship is, and what is the sort of series of events that led up to this point where Lucy actually needs to be freed from something. And so if we're looking at these creative contexts, we run into a bunch of challenges on both the language side as well as on the machine learning side. So if we look at language, we have these character-centric narratives. So we have characters, they have different properties, they interact with other characters in different ways. And we also have a plot, right? We have a narrative, there are different events that are happening that change the way in which these characters are interacting with each other and interacting with the world. And these are sort of things that you would not find in like a news article. Well, at least not to the same degree anyway. Finally, there's also a lot of inferences, like common sense inferences, that require world knowledge on the part of human readers to understand all of the different scenes that are going on in a creative text and integrate them into a coherent storyline. So these are sort of some high-level challenges on the language side. On the machine learning side, it's hard to formulate some of these problems into the traditional like input-output pair framework from the tasks that I've shown before. If I want to do something like narrative understanding, how do I collect labeled data for this task? In general, some of them are so complex that we have to resort to like unsupervised learning. And if we do that, then, well, we need some part of our model to be interpretable. We need to be able to look at the output of our model and compare it to what we or some literary scholar knows about these works to evaluate how well we're doing. And so these are the sort of main challenges that we're looking at here. And just to motivate why we should care about creative language, there are three, I guess, categories of that could benefit from something like this. So on the humanities side, there's something called distant reading in the digital humanities, where people build these computational models that take in a whole bunch of creative text as input, and they're tasked with extracting sort of examples of particular that disprove or prove a particular hypothesis that a literary scholar may have. And so these distant reading tools dramatically speed up a researcher's workflow if they're powerful enough. On the machine learning side, as I'll talk about in the rest of the talk, we're looking at, in some cases, totally new tasks, and we need to build new architectures to solve these tasks. And as we push towards like general natural language understanding, creative language contains some of the most complicated language. And so this is definitely a domain in which, if we want to make progress on this direction, we need to work on. And finally, at the end of the talk, I'll discuss how we can connect some of this work to human interaction component with things like conversational agents. Okay, so this is a sort of outline for the rest of the talk. I want to begin, and so all of these projects will touch on some subset of these challenges on both the language side and the machine learning side. I wanted to start by presenting a sort of case study on deep learning for question answering. And so the purpose of this are, there are two purposes. One is to introduce a concrete task where if we were able to understand creative language, we would actually be able to improve the downstream performance on this task. And second, I just wanted to give a better idea of the sort of work I've done early on in my PhD on question answering, and introduce some of the models that we'll be looking at for the rest of the talk. Okay, so the particular task we're looking at here is called Quiz Bowl, which is similar to Jeopardy in that it's a trivia game where there's a moderator who's asking a question to a bunch of competitors. And the questions are about famous entities. So it may be like a famous book or character or battle or something like that. And so we developed this deep learning system called Quanta to play this game. And before I go any further, I just wanted to give a more concrete grounding of the problem. So I have an example of a Quiz Bowl question here that I will read to you all. And if at any point while I'm reading it, anyone here knows the answer, just raise your hand. And if you're correct before anyone else, you will win nothing. Okay. Part of this book consists of a captain's log in which the captain reveals how his ship's crew disappeared one by one as they transported some boxes filled with, yeah.
This is Dracula, right?
Yes, it is Dracula. Well, that was very good. I did foreshadow this with my examples from earlier, but that's probably the earliest anyone has ever. Okay, anyway. So if you read like all of the clues here, you notice that towards the end of this question, the clues become very obvious. So if you've heard of this novel Dracula at all, by the final clue in this question, you'll be able to get the correct answer. Whereas if you are at the first clue, if you've only actually read the book and are familiar with the plot, like clearly you have, then you'd be able to answer this question here and get the points. So the task is not only figuring out what answer to give, but also when am I confident enough in that answer to actually give a guess. Yeah.
So, are people given some options, or is this just...
No, they're not given options, but we treat this as a classification problem. So there's only so many entities that are like famous enough that they could be asked in this sort of game format. So in practice, there's about 5,000 or so unique answers. Yeah. Okay, so right, we framed this quiz bowl question answering problem as a, just like before in our, when I was introducing those NLP applications, I take some clue as input and code this using a neural network and have it predict the answer. And so I wanted to go in a little bit more detail on the work we've done in the step and what sorts of architectures we've used, and describe some sort of insights that we've gained from experimenting with the different architectures we've used for quanta. So before I start, this is probably familiar to everyone, so we represent words as our basic units of text here for our quiz bowl clues as embeddings. And so what we're concerned with is this process of composition, because a question is not just a single word, but multiple sentences long. And so we need a neural network that's able to learn this composition function to take this sequence of 4 word embeddings and transform it into just a single vector representation that we can then use in downstream tasks such as question answering. So we'll look at 3 different architectures that we've experimented with for this composition function. The first is super simple. It's not even a deep learning model. It's just an element-wise vector average or vector sum, followed by a softmax layer to predict the answer. And so this model has no nonlinear transformations between the input and the output. It's very simple. We made one change a couple years ago to this model where all we did was just add some feed-forward layers between this average and the end classification layer. So we call this a deep averaging network, although it probably shouldn't even have a name. It's so simple. And finally, we moved to, so these 2 models don't take into account word order at all or syntactic structure. But we moved to this sort of dependency tree-structured neural network where the structure of the network is based around a dependency parse of the sentence. And so this parse tree sort of guides the order of the compositions that are happening in this phrase. And so this type of model was very popular like 3 or 4 years ago and has since pretty much fallen out of favor, replaced by LSTMs. But one key insight that we were able to gain from these experiments is that this syntactic structure actually doesn't give us as much as we thought, as we initially thought. So if we look at, yeah.
Previous slide. So here, all the edges, they share the same sort of weights. And
yeah, that's right. Sorry, I didn't show the equations, but there's, there's just basically one parameter matrix that, so actually in this case we untied this matrix, so we have a different one for every dependency relation that exists. But yeah, it's not like there's a unique set for every edge. Yeah. Okay, so we tried all these 3 models on 2 different tasks, so quiz bowl as well as the Stanford sentiment data set, and we found that actually, the nonlinear transformations have a much bigger impact on the accuracy than this additional syntactic information. And so since this work, there have been a couple of other papers that showed similar results for tasks like entailment and sentence similarity and a couple of other tasks. And so one observation we made is that actually one question that these results basically produces, like how much does word order and syntactic structure actually matter for many of these common NLP tasks, and that's something that we're exploring now with ongoing work on human experiments. So if we give humans like a jumbled up version of the input for any of these tasks, how well do they do? And it turns out that We haven't completed this, but humans are actually able to do very, very well on these jumbled up settings, which suggests that there might be some sort of unscrambling process that's happening in our brains. So it's not directly comparable to these bag of words models, but still pretty interesting. So anyway, back to the general theme of this talk. So we exhibited our quanta system against human opponents, and we were able to defeat Ken Jennings, who's a very good trivia player, the highest earning Jeopardy player of all time. We beat him pretty convincingly. So at this point, we were ready to consider Quiz Bowl essentially a solved problem. Humans are worse than machines at Quiz Bowl. But the Quiz Bowl community wasn't very happy with the statement. They said Ken Jennings isn't the best Quiz Bowl player ever. We have elite Quiz Bowl players. Quiz Bowl is different than Jeopardy, and so you should only make this claim after you've defeated a team of elite Quiz Bowl players. So we were very confident. We said, all right, we'll do this, and we'll definitely win. But it didn't go so well. So we actually got crushed by this team of top Quiz Bowl players. And so at this point, we had to reevaluate and sort of retract our claims. We did an error analysis and found that all of our points here came from history questions and science questions. We actually answered not a single literature question or fine arts question against this. Yeah.
How is this exact evaluation done? Because like Quiz Bowl is not like Jeopardy where we have to wait for the answer, right? You can buzz in as soon as you know.
Right.
So was this modified so that people, was it the same thing? So that, because the computer would have...
Yeah, so I've sort of not talked about this in the talk, but we present our input to the model word by word. And so at every point, it not only has like a distribution over the guesses, but it also has some confidence in how much am I willing to make a guess right now at this spot.
But was it somebody reading out the question? How was it synchronized?
Oh, I see. How are these things organized?
Like how are they synchronized between the humans?
Yeah, so there would be one person reading, and then another person on a laptop would be like pressing like an arrow key every time the person would read it. So yeah, that's not ideal, but yeah.
The human latency.
What I was kind of getting at is, did you guys know most of the answers, or were the answers and the humans were faster, or that you... Like, were the humans better at partial questions, or like, if you had waited to the end of the question, would you be able to get most of them correct, or was the...
Yeah, that's right. Yes, that's a good question. So yeah, by the end of pretty much all, like 90% of the questions, basically all the ones that are in our training set, we'll be able to get them by the end. It's just that these players are very good, so they get them after like the first clue or the second clue, and the computer needs more information there. Yeah. So that's sort of what we were exploring, is why are we so bad at these literature questions? And we were pretty much getting crushed. We have no chance of getting them after the first clue like you did. And so to actually understand this, when we did our analysis, we found that the system was essentially just memorizing named entities. So if I have a clue like this, where I have these two names, Renfield and John Seward, it's very easy once I see these entities to just say, oh, well, that's like a one-to-one mapping with Dracula. There are no other books that have these two characters. And it's very common for the later clues to contain a lot of these named entities. But if you contrast this clue to the first one here, where there are no named entities, and not only that, they're not even any really rare words here. So we actually have to do better than just memorizing entities. We have to fully understand this question, so a bag of words model isn't really appropriate here. And we also have to understand the source material. This is not something that you would find described in like a plot summary of Dracula or a Wikipedia article. It's sort of a more obscure plot point. And so this is sort of a connection to the rest of the talk, is that if we want to actually improve these systems such that they're able to answer this type of question, they actually have to have read and understood in some sense the actual source text that the questions are referring to. Yeah?
Reevaluate, did you go back and then reevaluate the bag of word model compared to the other sort of models?
On these earlier clues? Yeah, so we did this a couple of years ago, and we found that there was a much bigger, well, okay, not much bigger, but relatively bigger improvement on the earlier clues than there was at the end, where all of the models can just memorize things. But the problem is that we don't have like in our training data, we might only have seen this clue. We might never have seen this clue. So that's the bigger problem. Even if we're able to understand what it's saying, we may not know what it's referring to. Yeah.
So sorry, the next slide. So how did you come to this conclusion? Why not more data or?
Well, more data would help, but we are limited in the amount of data that we have. It's created by these college students and high school students. So every weekend they write like a couple of these questions, and so we have about 100,000 now of these quiz bowl question answer.
Really the current hypothesis.
Yeah, that's right. Yeah. If we had a lot more data where like all of these minute points were described, then that would also help, definitely. Yeah.
I was also trying to understand the training setting in Quanta. So was there, while training these models, was there more preference given to some kind of ranking where to make the system get the right answer just from fewer clues, or was all the text given in the beginning to train the model?
Oh, so we train the model with these partial context as well. So we give it like, I think the first sentence, the second sentence, and so on. And then we also train like the word by word model as well. Yeah, and then we had an additional model, like a buzzing policy model, where we actually had human data on when did the human buzz in here. So then we could train this this model to decide when to buzz and when not to buzz, depending on like, would I give my guess after the human or before the human? So there's like a reward here. Yeah. Yeah.
And did the system get to read these texts somehow, right? Because like, how would you know that about Dracula unless you had the full text of Dracula that you
That's right.
peruse? I mean, unless you had a fantastic Wikipedia plot summary that happened to include that minor point or something. But were the full text of these novels available somehow?
Yeah. So I don't think we actually tried just like dumping them all in with the label of the book, but we actually did do this for poems because they're much shorter, and it actually helps get it like string matches if there's like a question that quotes a line of a poem. But this doesn't work for the longer text. So we need like some sort of summary of the, yeah.
On the quiz bowl work, there is though these sort of Wikipedia summaries and whatever of the books.
That's right.
And so even if you had never seen a training example with the answer of Dracula, you could still get it correct, right? As long as so what you're learning is how to match the quiz bowl question to the summary text.
Sure.
But you could also match sort of to previous questions that have the same answer, right? So it seems like it's learning two different.
You mean if we use additional Wikipedia data?
Yeah,
or?
I mean, in the what you've shown so far, was that using any?
Yeah, so those results were not using Wikipedia, but we had an additional setting where we were able to get some slight improvements by. I think the one we actually published was just taking selecting sentences from Wikipedia articles that we think contain a lot of content that might be useful for answering these questions, and then labeling them with like the page title and then feeding them in as a question answer pair to our model. But we had like additional challenges where these questions obviously can't mention their answer in the text, and Wikipedia articles have no such constraints, so we had to sort of rewrite these things, and then like things became ungrammatical, and there's all sorts of issues like that.
So before you were feeding in this Wikipedia stuff, you could only give an answer that you had already seen in your training set.
Yeah, that's right.
Okay.
So we've tried some other ways to add like new answers to this our existing training set after we've trained the model, but so far they haven't really worked out.
Yeah. Okay.
Yeah.
But couldn't you have just trained a sequence of Beggar words models on a book, going chapter by chapter or even parts of chapters, and then compared that way? Because then you would have the words like captain and earth and box and disappear showing up with high probability in a certain area of the book, and probably other books don't have that, so you would be able to say.
Yeah, I mean, it may work for this setting if you think like Captain and Earth are unique enough to this book, but you can imagine if it's describing like an action so if it said like,
Right.
Yeah.
It's not going to work all the time.
Right.
But it seems like you should have some sort of a grounding that's covered the whole book.
Sure.
Even in a very coarse way.
Yeah, we haven't actually tried that, but we could. And some of the stuff I'll talk about is sort of in the same vein, except instead of a bag of words, we're sort of extracting a higher level summary of what goes on at every point in the book. Yeah. Okay, great. So I'll move on then to the first project on creative language understanding. So here we're trying to answer this question of how can we describe a fictional relationship between two characters in a novel? And so I guess the simplest thing you could think of to do for this problem is to treat it as like a binary classification problem. Are these characters friends or are they enemies? So it's sort of positive, negative. We could collect some data, annotate it, and train like a classifier, but this ignores a lot of the complexities in fictional relationships, specifically a temporal dimension. So if we look again at this Arthur and Lucy relationship in Dracula, this sort of demonstrates this problem where they start out in a very positive relationship. They're about to get married. They're in love. But eventually, Lucy is bit by Dracula, who's a vampire. So she falls ill, and she eventually dies. But of course, she's not actually dead. She turns into an evil vampire herself and starts attacking little kids and generally causing a lot of havoc. And at the end of this relationship, Arthur has to stake her through the heart and murder her. So you can see that this is not, it doesn't fit into the positive, negative categorization. There's actually this trajectory of the relationship that's describing its sort of eventual downfall. And so another interesting thing here is that we have states that represent the relationship, such as sickness and death, which are sort of important plot points that describe how this relationship is changing, that we wouldn't really get if we stuck to a set of predefined states like positive and negative. So our goal here is to learn these relationship states as well as this trajectory, an assignment of these states at every point in the relationship. So just really quick, I mentioned this distant reading motivation before. This model in particular could help answer these sort of well-studied questions. Do Jane Austen's protagonists have patterns in how their relationships develop? Do they start out hating each other and eventually get married? It's a pretty reasonable hypothesis. And maybe more interestingly, can we detect subtext underlying different events in novels and how that predicts events in the future? So we've actually been collaborating with an English professor at Maryland on this exact problem without much success so far, but it's definitely something that's interesting to humanities scholars.
So why do they call it distant reading?
Because, I guess the contrast is to close reading where you take like a paragraph of a book and just look really closely at the word choice and like how this was structured. But in distant reading, you're not doing this. You're more focused on extracting high-level summaries from a huge collection of books. So you're not really going in and understanding everything at that fine-grained level.
That's how people that reviewed this.
Or high extreme close reading of a small passage.
Okay, so to study this problem, we had to collect a data set. So we took about 1,500 novels, and for each novel, for every pair of characters that interact in this novel, we extract all spans of text in which they interact. So I define interaction here as any span of text which contains a mention to both of the characters. So this is the relationship between Ignatius and his mother, Mrs. Riley, in the book A Confederacy of Dunces. You see in the span, there's 2 mentions here, and I can extract all such spans and order them like how they appear in the book. So here I've just shown these explicit mentions, but in practice we run a co-reference system over the book, which isn't very reliable, but we're able to get a lot more of these interaction spans that way. So once we have this, our goal is to learn these states from all such spans in our data set, as well as for each relationship, a trajectory over this particular sequence of spans. So now we can get to the model. We call it the RMN, Relationship Modeling Network. In principle, it's a recurrent autoencoder that uses dictionary learning to reconstruct its inputs. So I'll sort of unpack what each term here is referring to. The dictionary learning part, we have this matrix where we want each row of this matrix to correspond to a different state. So the first row here might be sadness or violence, the second sadness, and so on. I'll talk about how we actually interpret these rows a little bit later, but for now assume that that's what we want to get out of the model. The second part is that we want at every span of text in a relationship, we want an assignment of the rows in this matrix. So we look at this as a probability distribution over the rows in this matrix. So if I have this span here where Ignatius and Mrs. Riley are sort of showing affection to each other in a strange way, we may want the love state to be highly weighted, whereas the violence state is pretty low. So that's what we want to get out of this dictionary learning part.
So is this going to be supervised? You're going to have labels like this?
No, we don't have labels. I'll talk more about this. So the recurrent part comes in where we aren't just interested in learning this assignment for a single span, but rather the sequence of spans. And so, all right, you can ignore that. The point of the recurrence is to basically smooth these trajectories so that if these two characters are 70% in love at time step t, I don't want them to just immediately fall to like 0% in love at time step t plus 1. I sort of want this more gradual change. So we use this recurrence along with some modifications to the update equation to ensure the smoothness criteria.
Is it really true?
Yes.
Is this a smoothness assumption?
Oh, yes. So, well, okay. You can argue that it's not always true. I mean, that's certainly, it's not always true, but...
You haven't seen Bollywood movies.
Well, I have. But, yeah, so so we initially tried this without this recurrence, and what happened was we got these very, very choppy things where we couldn't interpret them. So the only way that we could do this is to...
But you could do it sort of the vision way, that you have piecewise smoothness and
Yeah,
then you have,
that's
and then you
what I
have
was-
edges and so on,
Sure.
Yeah.
drops and so on, continue, yeah.
That's right, yeah.
But overall it's smooth, but there are occasional jumps.
Was it actually explicitly encouraged to not change from the previous thing, or was it just...
Well, actually, we sort of ended up doing an interpolation between the previous state and the current state in addition to our... so I'll show this.
Was that just to actually get the visualizations, or was that actually during training?
It was during training.
Okay.
We allowed the model to learn like the interpolation parameter, so it had some ability to become choppy if it wanted to, but in practice it rarely did this.
This is also assuming that these books follow sort of a linear type
Yes,
of
that's right.
progression. If there is a flashback or
That's
something.
right. That would break our visualization, and we acknowledge this, but it's really hard to detect when that's actually happening in these books, so we ignore it for the time being. Yeah.
But even if that happens, you're still in the flashback for a little while, so you still have multiple time points where the emotion doesn't change much.
Yeah, that's right. Well, yeah, I guess it depends on the duration of the flashback. Another concern is that for novels with a whole bunch of characters, so for example, War and Peace has a lot of characters with the same last name, and so our co-reference system sort of breaks here, and the visualizations we get are not very interpretable because we're not sure which character is being referred to. So this is another problem. But yeah, I'll show some results later. Finally, just wanted to mention that we don't have any labeled data, so we treat this as an unsupervised problem, autoencoding problem, where we're trying to reconstruct these input spans using a linear combination of the rows in this dictionary matrix.
So you're really trying to reconstruct every word in the...
No, so I'll go into more detail in the next slide. We'll look at the computations that occur at a single time step here. So the first step is to get some representation of the words in the span, so we just use a word embedding average. The spans are about 200 words long, so we decided that, well, when we did experiments with like LSTMs, we didn't really see any big changes here. I think our dictionary states are at a high enough level that the word order here doesn't really matter. And so the second step, we incorporate more global information. So we learn separate embeddings for the different characters in the book as well as the book itself. So the idea here is that if we have this embedding for Ignatius, it's supposed to encode global properties of Ignatius, like maybe the fact that he's rude to everyone he interacts with, regardless of who they are. This is sort of a global property that would affect the word embedding average representation here. We merge all of this in a feed-forward layer. And then we get to our recurrent connection. And so you note that we have this interpolation from the previous step, and this alpha parameter here is learned. And we also, interestingly, use this softmax activation as our nonlinearity, which is pretty different. Most RNNs just use TANH or ReLU or so the idea here is that we want to interpret our states as probability distributions. So if we do this, we can actually get our hidden state looking something like this. And then if we multiply it with our dictionary matrix, so this global dictionary matrix, essentially we're taking a weighted average of the rows of this dictionary matrix using the probabilities as weights. Now we get a single vector representation, which we try and make as close to this input word embedding average as possible using some max margin objective function. And so the crucial part to making this whole thing work is that we use these pre-trained word embeddings and fix them during training, so they can't change. If we didn't do that, then this model would just degenerate into like everything's all zeros, and that would be a trivial minimization of our objective function. But if we fix them, then what that allows us to do is actually interpret each row of this matrix, because the rows during training sort of fall into the same vector space as our original word embeddings. So what that means is if I have my word embedding space, so here's a simplified version that looks something like this, and I want to interpret the first row of my dictionary matrix, which I'll represent with this green dot, I can plot it in the same space. And look at its nearest neighbors. So here it would be guns, grenades, and bullets. And so I can do this for all of the rows in my dictionary matrix. And so now this starts to look a lot like a topic model. For each row here, these nearest neighbor lists sort of analogous to like a topic word matrix. And so after training, we get these nearest neighbor lists for each row, and we label them just like people label topics in a topic model. We manually go in and assign a single word that represents the theme of the nearest neighbor list.
So how do you know you're not getting the topic model?
What do you?
Like this whole recursive network,
right?
You could have just trained a topic model on all of the sentences.
Yeah, so we actually do that and compare it and yeah.
Were the human using a fixed set of labels? Were they picking from a fixed set of labels? Were they creating labels?
Yeah, so so a lot of them are sort of universal. So it wasn't, the humans were actually us and our lab labeling these things. We labeled this model as well as our topic model baselines in the same way. So a lot of the states were shared across all of the different models. So things like, I don't know if any of the ones here, but sorry, if you look at these examples here, there's a common like outdoors state, which both the topic model as well as the deep model learn. And so we try and be as consistent among these similar states as possible across all of the models. So in this result, we're showing we had 50 different states. We tried different configurations of 10, 30, and 50. But we found that if we use more states, we get sort of more interesting distinctions. So in the 50 state model, we learned 2 different types of love. Like one is a family love, and the other is a romantic sort of love. And actually, if you look at these results here, this baseline was our topic model. It actually has some idea of the sequence of its input as well, which makes it a reasonable comparison. But you can see that it focuses primarily on these sort of concrete topics like food and boats and outdoors. And in practice, we find that it doesn't really learn any of these emotional states that the...
Was it also running on the same sentences?
Yeah, the exact same.
Exact same sentence?
That's right.
It wasn't running across the whole book. Whereas the first one was running only on the paired entities.
That's right. Yeah, it's the same input for both models. Yeah.
So why would there be a difference?
Well, so one difference is that we have a bunch of external knowledge injected into our model through our word embeddings. And so the way that we're interpreting these things, you see these sort of words like regretful and rueful that are fairly rare, low frequency words. Whereas topic models, when you look at them, it's very common to have like very high frequency words as high probable in your topic. So that's one reason. Another reason is that we apply a penalty term to the rows of our dictionary to force them to be as different from each other as possible. So this also encourages sort of unique states as opposed to in a topic model, one common fail case is to have a bunch of duplicate topics learned.
So it doesn't sound like the recursion actually helped. It's
Well, I haven't gotten to that yet. Yeah.
So in a system that is discriminatively like learning the input, I understand that it can easily learn how to ignore like function words and stuff like that. But in your case, you were like treating all words equally, and there was no
That's right.
discriminative power to do that. So I don't like, how did it not just become degenerate? Just like,
Well, if you look at what happens here, you can. Oh, I see your point. Yeah, but it doesn't happen. So I guess because of the transformations that happen after the word average, it's able to basically ignore the.
but it's just an average of embeddings, and you don't
That's
allow
right.
those to change, right? So
Right.
like, the vast majority of the mass in that thing you're trying to predict is going to be things that aren't relevant.
Sure, but like the additional layers will probably focus on the useful information, right? And
Well,
tease that out.
It's not really discriminative in that way, right? Because you're trying to reconstruct an average of pre-trained word embeddings where the vast
Sure.
majority are going to be function words and irrelevant words to this topic, right? So like the one or two words. Like,
Okay, sorry. Okay, so the correct answer to your question, I blanked out, is that we actually filter the spans here
Okay.
to get rid of stop words and things like that. Yeah, I totally forgot.
Do you
Right.
do it for the topic model?
Yeah,
itself?
yeah, same thing in the topic model. Yeah.
So, sorry. I think the relation with topic models is interesting. Is there a neural topic model concept that uses embedding?
Yeah, so
It seems like that's exactly what you've done.
that's right. Yes, there's one by Raj Das, who's now at UMass, but he did it. He was Chris Dyer's student and had this neural topic model where it was essentially just a topic model that used word embeddings as additional inputs, and we actually tried to run that model on our data, but it's super slow to I mean, it's probably comparable, but because a lot of our gains here over traditional topic models are due to the word embeddings that we're using. But then we also had these additional, like we have a sequence that we want to learn a trajectory over, and so this is just a more natural way of encoding this
Why
domain.
is it called neural topic model? Word embedding you can get without neural networks,
Sure.
just by concurrent statistics.
Oh, you mean this other work?
Yeah.
Yeah, I'm not sure if that's what it's called. It might just be called a topic model with word embeddings, but yeah, that's the general idea. Okay, great. So now to your point of looking at the actual recurrence and if it helps. Here's just one, going back to our Arthur and Lucy example, we know the ground truth looks something like marriage to sickness to death to murder. So here are the trajectories that are learned by both our models. The left one is the RMN and the right one is the topic model. And so you can see that the RMN starts off pretty poorly with boats that doesn't represent the relationship at all in any way, but quickly switches to love and then sadness and then suffering and eventually ends in murder. So it's obviously not perfect, but it's doing a pretty reasonable job of following what we would expect it to do. Contrasted to the topic model, it's very smooth, but it's just stuck in this love state throughout the relationship. It's ignoring all of these important plot points like Lucy turning into a vampire and becoming evil and getting killed by Arthur at the end. And so we did this evaluation where we showed a visualization like this with these two trajectories to crowdsourced workers and asked them, here's a plot summary that is highlighting these two characters' relationship. Which of these two visualizations does a better job of capturing this relationship? Obviously this isn't a perfect evaluation, but more than 70% of the time, the workers preferred the RMN's trajectory to that of the topic model. So,
Was this generally the case across novels that the topic model was more smooth? Because that seems backwards from what I would have expected.
Yeah, so I mean, this isn't a normal topic model. It has this constraint of smoothness, just like our yeah. And so we did tune this parameter, but yeah, I think in pretty much every case, it preferred to just stick to one state for the duration. Yeah.
With regards to the relationship, the RMN is going from relationship like love and sort of
Right.
sadness and suffering and murder, but then suddenly there are these things like outdoors and boats and
Right.
stuff, right? So there's a very big shift in
Yeah, so
context.
actually this is, one reason for this is just due to the way we're visualizing. So we're just taking the argmax state of our distribution at every time step. So it might be the case that outdoors and sadness only differ by very little mass, but it changes drastically in the visualization. So initially we tried visualizing the entire distribution, but obviously this is hard with 50 different
If you have
states.
a hierarchical topic model, right? If you have a hierarchy and
That's
you
right.
sort of say, okay, here are sort of higher level
Yeah,
concepts.
so that's a good point because we actually developed a hierarchical variant of this model that I haven't shown here, but basically instead of learning a dictionary matrix, it learns this tensor, and so it has to select a slice, and then within each slice, select a row. And we didn't actually do this evaluation for that model, but it's possible. It's probably a better way, yeah.
I mean, could you also change it so that it's not like, because the system really has the system's just trying to predict the thing that's the content words, right? So
Right.
if a bunch of part takes place on a boat, it's going to
That's right.
predict boat, but we know as humans that boat is not a relationship.
That's right. So you could filter out more, yeah, with more precision, I guess, if you knew what you were looking for. And so this is something that, like, when we're working with the English professor, she has an idea of what she's looking for in the book, and these global themes like sadness don't really interest her very much, as you can probably imagine. So we have been trying to, like, initialize the rows of this matrix with things that we know, and then try learning the model afterwards.
So the themes are supplied. So who comes up with the themes now?
In this case?
Yeah.
Yeah, so the English scholar will have some idea of what he or she is interested in.
But for your current visualization,
Right.
Who came up with?
Oh,
both
so
now?
these are the labels that we assign to these nearest neighbor lists. So there's no nothing from us that's coming into this other than these labels.
But the labels.
But like if we knew what we were looking for here, then we could just replace this with like something that some words that we're looking for, and then train the model that.
So is the goal here that if you're only looking at these paragraphs where two entities are present, and you look across many, many books,
Sure.
that things like boats and outdoors are eventually going to fall out, and the only thing that's going to remain is relationships?
Well, so we don't have such a constraint right now. So
No, but this is completely unsupervised.
yes, that's
Except
right.
for your labeling at the end.
That's right.
So is it, or shouldn't be one of the goals to show that you do extract relationships this way? You learn what a relationship is.
Right.
So have you tried to evaluate that? Like what
mean-
percentage of things that you're coming up with is
I
really
see.
a relationship versus
Versus like
place?
more. No, we haven't looked at that. But yeah, there's, as you can see, a mixture of both. I'm not sure what the proportion is either way. And we really didn't want to just throw things out, because it is sort of interesting that boats is even learned here. Maybe boats are very common in like novels and such, and maybe they'll tell you something about.
That's where the love starts.
Right, maybe.
It would be interesting if basically there was a thing where you have a ring, right, in a relationship, and you
Right.
say, okay, now the ring event happens, and
Right.
so
But the ring is then sort of relationship, right?
Yeah.
The boats maybe.
Yeah.
But it would be interesting if you trained a lot of things and then in the end you analyze it and say, well, this is what you get. If you analyze only parts where you
Right.
have named entities, well, person, two people in proximity, then you extract lots of relationships. If you look at the rest of the book, where
Sure.
you don't mention two people, but just single person,
Right.
you get a lot of the places or
That's right.
other sort of actions. So that would be interesting just in an unsupervised way to analyze what sort of things.
Yeah, definitely.
Is this neural architecture novel as a topic model in general? Like, have people done the same? Because it seems like the relationship part is a little bit arbitrary. Like, you could do this.
That's right. Yes. So this is, yeah, to my knowledge, the first time anyone's done this sort of dictionary type.
Have we tried
thing.
it without the relationship part?
Yeah, we tried it actually initially as just a general purpose topic model. But yeah, then we switched over to this.
Did it work really well?
Yeah. So the topics it generates are much more coherent than what you would get out of like LDA. But yeah, one trouble is that these distributions are usually much smoother than. So in like a topic model, you get a very high probability on just one topic, versus here it's a lot flatter, and so
you can kind of control that with a penalty,
right? We tried, yeah, with the temperature parameter and so on, and now there's other things that you could probably use here. So. Yeah. Yeah. Okay, so I've spent a whole bunch of time on this project. I think I have like half. Okay. So maybe I'll just go on to the comic book part of this talk and try and go a little faster. So here we're switching the focus from characters and onto the inferences that we need to make in order to understand how two scenes come together to form a coherent story, or multiple scenes, not just two. And so we're looking at this in this multimodal domain of comic books where we have both artwork as well as text in the form of dialogues. But I just wanted to give an example of how this occurs in language. So if I have these two sentences, Lex Luthor's limousine came late today, the driver had overslept. To understand what's happening here, I have to make these two critical inferences. So I have to first understand that driver in the second sentence is referring to the driver of the limousine in the first sentence. They're not like two completely separate things. And also that oversleeping is a common reason for being late, right? This is also not unrelated to the first. So this sort of thing happens all the time in language, but it happens literally all the time in comic books where we have panels. So here's an example where I have these two panels. On the right here, we have this big explosion. And to actually understand what's causing this explosion, we have to understand the conversation that's happening between these two men in the left panel where they're debating whether or not to blow up a roadblock. So from this conversation, I can infer that they did indeed decide to blow up the roadblock. And not only that, but in the time that passed between these two panels, they probably went and set up the charges and had time to huddle behind these rocks. And we can also infer that these two men are likely part of this larger group of men that's down here in the right panel. And we can maybe also infer that they're the leaders of this group of men. And you can, go on and on.
They're the ghosts.
That's right. They could. I guess they could. So you can go on and on making these inferences from just these two panels, but when we're reading this as humans, we don't really think about all of the different connective sort of inferences we're making. And so this problem has been studied in research on comic books, and there's actually a term for this called closure, which is the process by which human readers connect different panels together to form a coherent story. So we're interested in computationally modeling closure in comic books. So just like before, no one's actually looked at the content of comic books before, so we had to collect our own data set. So we take a bunch of comics that are in the public domain because their copyright has expired. So they're from like the Great Depression era and World War II era, but we have a lot of data. And so we create this data set, and now we need a way to evaluate how well we're doing. So we use this cloze style framework from linguistics where I have some context, like the job candidate's talk has been interesting so far. I hope the rest of his talk is just as blank. And then I ask a human to fill in the blank. So in order to do this task, I have to have some understanding of the context, and I have to be able to connect it to the different candidates to find the best one to choose, which hopefully here would be C. Okay, but this task actually looks different in comic books where we have 3 panels as our context, and we're asking the model to predict some aspect of the 4th panel that immediately follows this sequence. So here I have a sequence of panels from Alice in Wonderland, some old Alice in Wonderland comic where Alice and her friend are riding around on these cloud-type vehicles that are powered by sprinklers. And Alice's cloud malfunctions, so her friend gets out safely, but she crashes into this building. So that's our context. Then we give the panel that immediately follows and ask what goes into this dialog box here out of these 3 candidates. And so the answer here is C. But you can see that the candidates here are actually relatively difficult. So candidate A contains the named entity Alice, and the reason for this is that our distractor candidates come from adjacent pages of the comic book. So we would expect them to contain the same sort of named entities, maybe even refer to the same events or plot points. And so you really need a good understanding of this context in order to disambiguate between these different choices. So that's our task. So now I can move on to our model.
How
Yeah.
do humans perform?
Yeah, I'll get to that. So if we take our sequence of 3 panels here, which is our context, we use a sort of hierarchical neural network architecture to create a representation of this context. So we start, the first level is looking at each panel in isolation. So we have an LSTM that encodes the dialogue here, and we have a CNN that extracts features from the artwork. And so we initialize this CNN with a network trained on ImageNet and then fine-tune it for our comics domain. I'll show an alternative approach a little bit later. Yeah.
Is it straightforward to get the text out of these?
No, it's not. I sort of just totally ignored that. But the data creation was actually probably the most work in this project where okay, I guess I'll briefly explain. So a comic book comes as a zip file of JPEG page scans. And so we had to train an RCNN model to extract panels first from these pages, then another model to extract the dialog boxes from the panels. And now that we have images of the dialog boxes, we fed them to an OCR system to actually get the text. As you can imagine, dialog boxes from the 1940s are not very good candidates for OCR, but we actually found that Google's OCR cloud service was very good at extracting the text from these things. One reason could be that text in comics is all caps, so this could break the language models that people use, but it didn't happen for Google at least. So we have a lot of errors, but in practice, it doesn't seem to matter for humans, so they're clearly not like.
So the location of the panels. Okay, so the ID of the panel is also going into Z, like.
What do you mean the?
So you have 4 panels.
Right.
And then you have. And then you have these dialog boxes.
That's right.
And the locations of those dialog.
So what happens with our input to the CNN is that we basically draw black boxes around the dialogue, so it doesn't have any chance of like recognizing words if it were capable of doing that. We just wanted to make sure it had no capacity of doing.
But does it have a capacity of saying who said what? What was the object?
So we don't have those annotations. And I'm not talking about this here, but we tried some sort of attentional architecture that, based on the coordinates of the dialog box and the overall panel image, would try and focus on, because like for humans, it's pretty easy. We have this tail we can sort of follow it down, but we found that the attention was just focusing on random parts of the image. So still some. Yeah.
So you're using pure OCR for this. The image does not inform the OCR.
No.
So when the human baseline is actually much better than what is given to the signal, because the raw signal would be you're given two sentences, right? And you're shown.
No, but we give the exact same input to humans.
Oh, okay.
So the humans get the OCR stuff as well, and they get this blacked out dialog boxes, so they have to read it.
So they don't know what Alice was saying in the first panel.
Well, they know that this content should go. This dialogue should go into this first box. The model also knows that, but
how does the model know that? Yeah, that was my question.
I see. So the model just knows the order of the boxes. It doesn't know the location. So yes, this is one advantage a human may
order,
have.
like left to right, up, top down?
Yeah, there's a canonical order in comic books. It's a Z order.
If you blacked out these boxes and the CNN is looking at the image, which is edited this way, then it can infer things about.
That's right. Yes, we would hope that it could infer things like which character is, but I'm not sure if that's actually happening. And yeah, our experiments with it.
Is visual part doing anything?
Yeah, so that's a good question for the next slide. So I just wanted to briefly mention that we have this other network that's going across panels and integrating this information, and then we use it to score our different dialogue candidates. So yeah, just before I get to the results, sorry, one more slide. There's a key difference between the comic images and natural images, which is a sort of stylistic themes that the artist wants to follow. So these are all lions, but the ones on the left are from like more humorous cartoons. So you can see that they have like human type expressions, whereas the ones on the right are from adventure comics, and they're supposed to be more realistic. And so we have this additional dimension of style to worry about. And so initializing our CNN with ImageNet probably isn't the most optimal way to do this. So very recently, we've been trying, instead of ImageNet, to initialize with this colorization network, where we feed in the grayscale image of our comic panel and ask it to color it. And so this objective function forces it to learn a lot about like objects and structure within our own domain. And so
this is the Berkeley paper.
Yeah, the Rich Zhang's paper, yeah, from last year. Yeah, so we've had some pretty interesting results with this, and we're hoping to try and finally get the attention type architecture to work if we have a more powerful network here. So with that, I'll get to the results. The conclusion is that this closure problem is very hard for computers. So we have 3 candidates, so random accuracy is just 33%. If we look at just the image...
Were the candidates taken from any, was it literally over all 4,000 comics? Or was
No, so we had 2 different settings. One was the easy setting. The hard setting was we took them from adjacent pages of the comic book, so that was much more difficult. This is all on the hard setting. So if we look at just the image and ignore the dialogues, we don't do so well. If we reverse and we look only at the dialogue and ignore the image, we do slightly better, but we get this nice gain when we look at both the image and the text of about 12%. The problem here is that human performance is 84%, so there's this huge like 20% gap between the human performance and the best model that we had. And while some of this may be due to our visual features not being as good as they could be, a lot of it when we did our error analysis is just from to solve the task, you're expected to have some sort of external world knowledge or make some inference that you might not have seen in your training data or might not have seen enough times. So things like perspective shifts and zooming out of the camera are very common in comics. And so just learning that this is the same object in both of these panels, even though they're from different perspectives, is a very hard task. Yeah, to conclude, we're currently trying to both improve our visual model as well as trying to incorporate some of these existing databases of things like visual genome, which have been labeled for natural images, into our comic model. Yeah.
I was just wondering, did you try giving only the text to humans to see how well they
Oh, no, but we are in the process of doing this for our camera-ready version.
Okay.
Yeah.
I wasn't your reviewer.
Yes.
You would say
So
that.
on the ones where the humans, so how many humans per panel did you have? How many
We had
questions?
3 humans per task.
So on the ones where all humans did agree on what the right answer was, how was your accuracy on all of these different models on that subset of the data?
That's a good question.
That would be,
Right.
I think that's a better measure of, are we close to humans or
Yeah,
not close?
that's right.
Because then you've taken out the variability of the humans.
Sure.
And maybe it's a small subset, but it might be informative to look at just that subset.
Sure. Yeah, that's a good idea.
Yeah.
Yeah.
Have you done any nearest neighbor comparisons on your tuned image features to see, like, does it understand the concept of a lion across?
No, we haven't done that either. But yeah, that would be, because we don't have so the only way we can get labels is by looking at the dialogues. So if the way we
manually, like, take a picture of
I see.
line and then just see what
That's a good idea. So the way we were trying to do it was I can look at the dialogues, all dialogues that mention lion, and then so yeah.
So if you haven't looked at how image features are contributing, then I have a mean question.
Sure.
If you just use the size of the black box as a feature, how well would you do?
Yeah, so we tried this, and you don't get any improvement over the text-only model. Yeah, and so we also control. So one reason for this is.
Do you do as well in image only? If you just use the size of the black boxes as features.
Oh, I don't know.
Is that
we
all
tried
image
like
only
with the
does?
text-only and adding the additional box information.
Box size.
But one of the reasons why is that we control the candidates such that they're all about the same length, and so this sort of discourages very short candidates from being chosen.
Yeah, but you should definitely look at what are the image analysis provided.
That's true. Yeah, just the black box only thing would be.
Because that's typically what happens with image analysis. Like,
Okay.
I remember back in grad school, somebody made a data set of faces for face recognition, and with PCA you get 100%, and it turns out, well, they were taking images of different people in different offices and different things with a fixed camera, and they were making faces.
Right.
So it was just backgrounds.
Yeah, so we tried to control for all this, but
so
yeah,
if you don't look at what you're getting,
That's right.
it could be very easily just trivial
Yeah, sure.
inference.
Great. So, okay, I have like 15 minutes, so I'll try and speed through my future work part now. So the idea is that all of this stuff I've talked about up till this point has been focused on understanding what's going on in these contexts, either the characters, the relationships, the inferences we need to make to understand them. But we can sort of take the next step and go towards generation. So let's say I have some understanding of these high-level contexts. Can I actually use that information to influence how my, like a decoder in a sequence-to-sequence model should generate text? And so you can look at this in a sort of conversational framework where this is probably the simplest possible model where I have a sequence-to-sequence architecture. I take as input some utterance and try and generate an appropriate response. And so these things are trained on like chat logs or online message board forums. But they don't really have any understanding of context. So if you look at what these conversational agents such as Alexa or Cortana or Siri are capable of, they're currently just restricted to like these single turn questions. How much protein is in an egg? Add eggs to my shopping list. And these sort of very simple chatbot type things that take no contextual effort to respond to. So what we want to do is move to a more context-aware setting. So last summer at MSR, I worked with Scott and Mingwei on just this question-answering problem of if we have a follow-up question here, which here how many carbohydrates contains a sort of implicit subject of egg, which is in the previous question. How can we solve this sort of problem? And it turns out to not be very trivial at all. But I'm going to focus here on not just this immediate context, but sort of more high-level, discourse-level context. So what we'd like is for an agent to be able to model a particular individual user and have some understanding of the user's beliefs or how they interact with other people, and be able to adapt its output, what it's generating, as it gains more and more interaction history with its user. And so one point I wanted to make is that in creative language, so like novels and plays and short stories, we have a lot of human interactions. We have dialogue, say, but we also have descriptions of properties of characters, properties of the world, and how events happen that change the way in which characters are interacting. So this is a very rich test bed to develop models for this sort of high-level contextual understanding and how that influences language generation. So before I get into like a one potential problem that we could work on, I wanted to just mention briefly that non-goal-oriented dialogue, so not just answering questions or performing commands, but more sort of social chat-type language is also very important. The main reason is if we're looking at a sort of goal-oriented setting where maybe I'm trying to book a restaurant or something like this, if you look at human-to-human interactions, there's a lot of social content that happens that's interspersed with the just task-specific content, and this is shown to improve like user engagement and how they feel about this interaction. You can also think about the language learning perspective. If I want to learn a second language, the best way for me to do this is to speak to someone who's fluent in this language, but I may not always have such a person around, so an agent could maybe take the place of this, and obviously the final goal is just to keep people entertained or keep them company when they're feeling lonely. I just wanted to have one potential example of how this would work. So here's this timeline of our Arthur and Lucy relationship where I have the love state and the suffering state. And if we imagine a scenario where the user is playing the part of Lucy and the agent is playing the part of Arthur, now we can actually have some ground truth data to develop these models. So like in the love state, Lucy in the novel says, "I love you more than ever." So the agent should be aware of this context, right? It should be aware that I'm in love with Lucy. I should respond positively to this utterance. And in the book, Arthur responds, "You make me very, very happy. I don't know what I've done to deserve this." So we actually know what Arthur says in the book, which is crucial to being able to train these models. If you contrast this to a little later on in the book, after Lucy is switched into an evil vampire, she makes a similar sort of utterance in the suffering state. "Come to me, Arthur, leave these others and come to me." And the agent should at this point recognize that I'm no longer in a positive relationship with this person. She's no longer the person I was in love with. She's now evil and a vampire. And so I shouldn't say something like I said before where I responded positively. I should instead, in the book, Arthur says, "Is this really your body? You're only a demon in your shape." So definitely not a positive utterance here. And so you can see how this high-level context should be able to influence what this agent is saying in terms of content. This is just...
This should be super hard. This is like super high level, because "come to me" could easily be positive or negative, right?
What do you mean?
This dialogue, learning anything is very difficult. This is a very particularly difficult dialogue to
You mean this example here?
Yeah.
Yeah. Sure. It was hard to find an example from Lucy that was actually...
You could just run that. You can just condition Zoe, for example, a chatbot, to run through these phases, to be in love for a little while and then be...
That's true.
And then be suffering for a little while and be upset with you for a little while. And it would make it much more natural.
That's true. That may be a much more engaging chatbot. It had feelings of its own.
Hopefully it doesn't end in murder.
Right. Right. So... we also just don't want to restrict ourselves to language-based context. So you can imagine these agents having cameras in the future and being able to respond to visual cues as well. And so related to this in our comic book setting, we could, instead of trying to predict out of a set of candidates what comes here, actually try and generate it. You could imagine not just looking at 3 context panels, but much larger context history at a higher level, like in the relationship modeling.
Have you tried it? Or you plan to?
No, this is future. Right. And so another potential avenue of research here is to generate sort of structured responses. So instead of assuming that I'm just going to say a single sentence in response every time, I may want to generate multiple sentences. And if I'm doing this, I need to have some sort of coherent structure to what I'm generating. And so this is a totally different problem, but also something that is really interesting to me. And yeah, we can also do like image generation. This is sort of not really relevant here. Finally, I wanted to conclude by really briefly mentioning that style is also important in these agents. So these 2 sentences have the exact same content, but the one on the bottom is in a totally different style. It's in this long-winded legalese. The contention is that the context, my interaction history with the user, should also affect the way in which the agent is producing content. And so you may imagine like an agent that's able to mimic the speaking style of its user. This could lead to more engaging conversations. The user may be more likely to talk to the agent if they shared speaking styles. And so with this motivation in mind, I've been working on this sort of analog of this neural style transfer method in computer vision to text, where basically we have some content and we want to decode it into a bunch of different styles depending on some context. And so I've been working with Pushmeet and some other people on this project, and I won't go into detail because of time concerns, but basically we have the sequence-to-sequence architecture. We force the encoder to focus on content, and then we have some style author-specific parameters here in the decoder that allow us to essentially decode this content into varying styles. And to conclude, with models like these and projects like these that I've talked about, evaluation is a sort of big concern, right? In a dialogue scenario, I might have many different appropriate responses for a particular utterance, and so how do I evaluate whether my agent is taking this high-level context into account when it's generating these responses? And so human evaluation is a sort of huge component of any of these projects. Also the style transfer project as well. And finally, I had mentioned that one of the goals of moving towards this non-goal-oriented setting is it makes current goal-oriented settings much more natural if you're able to sort of intersperse more social content into there. And so how are we able to actually integrate the more conversational aspects with the more goal-oriented aspects without losing performance from the goal-oriented setting? And how do we sequence these conversations such that I get maximum engagement? So these are all sort of open questions that need to be resolved here. So yeah, that's about it. I think I took a lot more time than I intended, but if there are any questions, yeah.
So all the comic data is getting publicly released?
It is currently going through some, so we have like someone testing all our code to make sure it works, but it'll be released in the next week or so after.
With all the pre-processing of all.
Yeah, so all of the pre-processing, all the code for training our models and stuff. Yeah.
So the closure work on the comic is reminiscent of the Rochester short stories course.
Right, yes.
You get 4 sentences.
That's
and
right, yeah. That's sort of where we took our inspiration.
And so I was wondering, have you tried to generate the text for your closure image?
You mean instead of choosing from candidates?
Instead of choosing, have you tried?
No, we haven't tried that yet.
And I wondered if you combines the training data that you have in the short stories with the information that you have in the comic, could you get something?
Oh, that would be interesting. Yeah. Yeah, we should try that. One reason why we didn't do this is because we would probably have to use a character level model for generating the text. We have lots of entities and OCR errors and so on. So yeah, I think this is definitely some avenue for future research. Yeah. Yeah.
So I liked the motivation that you gave from that 1968 paper, that having some social interaction also made the task more goal-driven. I was curious, do you know if anyone has tested that with like a Wizard of Oz type of experiment with a computer, like a person interacting with a computer? Is it still true that we like having social interaction, or would we find it in...
I'm not sure. So there has been some work on trying to replicate this sort of adding social content as well as the task-specific content into these dialogue systems, but I don't know if that's preferable to humans from a computer as opposed to... It's certainly preferable when it's a human-to-human interaction, but yeah, I'm not sure. Yeah, I think a lot of it depends on like if a human is like perceives the computer as being limited in some way, like only focused on task-specific dialogue, then they may be less likely to, I don't know, have a positive reaction to social content from.
Well, and I wonder if you view if you're talking to another person, your kind of peers, if you're talking to the computer, it feels like you might see them as
sure.
Kind of
yeah,
your
that's right.
task giver.
Yeah, that's definitely
and then
possible.
it asking you about the baseball game last night might seem kind of annoying.
Right.
I just want you to do what I tell you to do.
Yeah, that's right. But I think as they become more capable, maybe this
Yeah,
dynamic
it might change.
Right.
I'm just curious if anyone had looked at that.
Yeah, I'm not
Okay.
sure. Yeah.
Have you tried the visual analog of closure? Like, let the model see the text but not the panel?
Yeah, so I didn't talk about this here, but we did do that as well, and we also did another maybe more interesting one where we showed them the 3 panels of context and then showed them the 4th panel, which had 2 dialog boxes in it. And so we would give the content of these dialog boxes, but ask them to sort of order the, so figure out which dialog goes into which box. So it's a reordering task. And one thing that we're planning to work on now is given like three panels of context, I'll give you the content of the next 3 panels out of order and ask you to reorder it. So this is sort of like a higher level, requires some higher level understanding. Great. Thanks.